Suppose that you have a function f of x that's equal to 3 to the power of x. We know that all the exponential functions are 1 to 1, so therefore it does have an inverse. So let's go ahead and try to find that inverse. The first step we're going to do is change the f of x to y, and we're going to say y is equal to 3 to the x. And then we want to switch our variables. So at this point we have the inverse function in implicit form. X is equal to 3 to the power of y. And then we have the task of isolating the y. The question is, how do we do that? I want my equation to say y equals, but it's in the power. And with the tools that I have at this moment, there's no way to do it. In the past, I've heard suggestions such as divide by 3 on both sides, but that's not going to get rid of our power of y. And multiplying by the x does nothing, dividing by the x does nothing. Well, we're still going to have 3 to the power of y. So how do I get that y out of there? We know that this function has to exist because my original function is 1 to 1. But what is that inverse function? Well, that's where this comes in. We're going to say y is equal to, and we're going to write log base 3 of x. What's that? What's a log? Well, that's what this whole section is about. Let's just finish this work. We're going to write as f inverse, and we have log base 3 of x. All right, let's go ahead and dig a little bit deeper into what logarithms are and what logarithmic functions are, and how do we use them when we know that they're the inverse of the exponential function. The key to our work is all in this step right here. Taking an equation that looks like an exponential equation and rewriting it as an equation that is a logarithmic equation. And notice the relationship of all the parts and where they've moved to. Let me write this again. I wrote it in the corner of our page using a base of a, because we won't always be in base 3. And this is going to be the definition of our logarithm as related to the exponential equation. Now recall that our exponential equation, written as f of x is equal to a to the x for any base a, that where a is positive and it's not equal to 1, then my domain is all real numbers and my range is positive numbers. If my logarithm is the inverse of that, then we're going to switch the domain and range. However, the rule for a is still true. Because the a has nothing to do with our domain and range, it's just the base of the exponent. It still is the base, it's just called the base of the logarithm. But the domain and range, notice how the values in the domain and range have switched with the exponential function. Now, I've stated that the logarithm can have any base that is positive, or as long as it's not equal to 1. But we also have some special bases that exist, so let me introduce you to them right now. E is our exponential number, and we use it so often that when we write log base e of x, that's just a lot of letters for something that we use very often. So you won't ever see anyone write log base e. What they really write is natural log. And since they write it in French, they say log naturel. So it's ln. And if you ever see ln of x, what it means is log base e of x. So since my base is e, when I rewrite everything, then I'm going to say x is equal to e to the power of y. And so these two statements are equivalent. Our next base is base 10. And when you write something as log base 10, that's also a lot of letters for something that happens very often. 10 is our normal standard base. We're in a decimal type of number situation. So when we have something like this, we just tend to write it as y is equal to log x. And when the base isn't written, it's understood that the base is that invisible 10. So since the base is invisible 10, you'd say x is equal to 10 to the power of y. For all other bases, you have to write it. So if you have something that's not base e and not base 10, then you have to write the base in there so that we know what base you're working in. This statement, y equals log base a of x and x is equal to a to the y power, works both ways so that we can simplify either exponentials into logarithms or logarithms into exponentials. Let's get some practice. Here is an exponential statement. A to the third power is equal to 2.1. The base of our exponent is a, so that's going to be the base of our logarithm. So you could write log base a of 2.1 is equal to 3. Our next question is e to the power of 2.2 is equal to capital M. You have to make sure you're using lowercase e and capital M when you rewrite this. And I'm going to rewrite it in a format that's never used. I'm going to say log base e of m is equal to 2.2. And you would never want to leave it that way because log base e is an appropriate way to write it. You're going to say ln of m is equal to 2.2. For question number 2, we're going to change logarithmic statements into exponents. Since the base of our logarithm is b, we're going to use that as the base of our exponent, so I'm going to write b squared is equal to 4. The next question says ln of x is equal to 4. I'm going to rewrite that as log base e of x is equal to 4. You don't need to write that. You should just think it really, but I want to write it down so you know what I'm thinking. The base of this logarithm is e, so then the base of the exponent will also be e. So I'm going to write e to the 4th is equal to x. The last question says log 100 is equal to 2. When the base isn't stated, then it's that invisible 10. And so since 10 is the base of our logarithm, we're going to write 10 to the power of 2 is equal to 100. If we're ever asked to simplify a logarithm and we don't know how to do it, sometimes we can just set it equal to a variable, any variable that you want, and then you can rewrite it as an exponential equation, and this would be base 8 to the power of k is equal to 8. And maybe when you write it this way, it might be obvious to you that the power on the 8 is 1. And what we learned last time was that when we have something to the power with the same base, then we could say that those powers are equal to each other. The next question asks us to find the exact value of this logarithm without using a calculator. Once again, we're going to set it equal to a variable, any variable you want, and then we're going to rewrite it as 1/3 to the power of m is equal to 9. And like I said, maybe we could write these as exponents with the same base. So this would be 3 to the power of -1 to the power of m, and the other side is 3 to the power of 2. And so that becomes 3 to the power of -m is equal to 3 to the power of 2. Now that it's written as 3 to the power on both sides, then I can take those exponents and set them equal to each other and solve. Log base 1/3 of 9 is equal to -2. Since I introduced the variable m on my own, it wouldn't do any good to say m equals because no one else knows what m started off as. So technically I should do that with the first problem as well. The last question is ln of e to the 3rd. So we are going to set that equal to j, and then we're going to say e to the power of j is equal to e to the power of 3. And we can see that they're already written with the same base, so you just take that out. So you just say j is equal to 3. And then once again, the j was not in our original question, so we want to restate it as ln e to the 3rd is equal to 3. When you introduce your own variables, you have to remove that variable from the final answer, since it was not part of the original question. Our next question asks us to find log base radical 3 of 9. So once again, let's just choose a value like c, and then we're going to rewrite this. The base to the power of c is equal to 9. And then we're going to try to rewrite this with the same base on each side. So that's going to be 3 to the power of 1/2 to the power of c is equal to 3 to the power of 2. And simplifying that gives me 3 to the power of 1/2 c is equal to 3 to the power of 2. And you want to wait until it's in this format where it's the same base on both sides with a power on that same base. And then you can remove that power and set them equal to each other. You can't do it until you're at this step. But now I have 1/2 c is equal to 2. So c will be equal to 4. So I have log base radical 3 of 9 is equal to 4. And then we have log of the cube root of 100. We can't simplify that easily, so we'll just set it equal to d. And remember, when the log doesn't have a base, that's a base 10. So I'm going to write that with a base 10 to the power of d is equal to the cube root of 100. And I want to rewrite that cube root of 100 with a base of 10. So the left side will just be 10 to the power of d, and the right side will be the cube root of 10 squared. And remember that cube roots are basically the power of 1/3. And so we're going to take those powers and we're going to multiply them. 2 times 1/3 is 2/3. And since I have both sides written as 10 to a power equal to each other, then I can say that d is equal to 2/3. So log of the cube root of 100 is equal to 2/3. This next question asks us to use our calculator to evaluate this. And this is really just an exercise in using your calculator. You make sure that if you're doing some fraction that you want the calculator to simplify, you have to include the whole numerator divided by the whole denominator. If you don't include fractions with parentheses containing your numerators and denominators, you're probably going to get the wrong answer when you use your calculator. So go ahead and type that in, and I can tell you that the answer is going to be 0.43429. And it keeps on going, but that's good enough for right now. Now if you're getting something different, then you're not typing it in correctly. And this is what it looks like when I type it in. I need to start off with parentheses, and I put log, and when I use the log button, it has a parentheses in it. I put 15, close my parentheses, say log, once again it doesn't open parentheses, I'll say 20 and close it, and then I need to close my numerator, and then I put a fraction line, and then I put this to open my denominator, so the ln of 15 plus the ln of 20, the whole thing will be in the denominator. Then I write ln of 15 plus ln of 20, and then I close my denominator. So that's what you should have typed into your calculator if your calculator is as old as mine. Some of you have newer calculators where it will display it so you can see the fraction and you know which part of the fraction you're putting it on, which is great. It's wonderful. But if you don't have that and yours is more like mine, you have to be careful on the way you type it in. And if you write it incorrectly, you're going to get the wrong answer. Also, if you don't show your work and you get the wrong answer, I can't give any partial credit. But if you show your work and then you accidentally type it in wrong to your calculator, then I know that you had the right concept and I can give you most of the points, and then it's just calculator error. But you have to make sure that you know how to show your work and that you know what these logarithms mean. The next few questions are going to be asking about the domain. And recall that the domain of the logarithm rule is that the argument must be positive. And that's the first statement I'm going to ask you. What is the rule for the domain of logarithms? But then after you write that the argument must be positive, you must take the argument of our specific function and write it as greater than 0. So for this question, it says ln of x minus 1. My argument is x minus 1. And I'm going to say it must be positive. And then solving this, I will say x is greater than positive 1. And if I were to look at a number line, that would be all these numbers. So that would be from 1 to infinity, not including 1. So there's my answer in interval notation. For this next question, my argument is 1 over x minus 5. So I'm going to take that argument and say it has to be greater than 0. Now, this is a rational function, so I want to take the zeros of the numerator, which there aren't any, and I want to take the zeros of the denominator, and I'm going to draw a number line. And at 5, it's undefined, and I only have 5 to break up my two regions. So if I plug in some number greater than 5, I find out it's positive. And when I plug in a number less than 5, I get an answer that's negative. So we're talking about not including the 5, but including the positive regions. This is going to be the interval from 5 to infinity. Now, being able to set up the first statement is in this chapter. Knowing that the domain of a logarithm means that you take the argument and set it greater than 0, that's what we're learning in this section. But everything in this orange box, anytime you have an inequality, whether it's rational or polynomial, you want to follow the rules from previous chapters. And so you have to remember, you have to recall some of that other information on how to do that. For this next question, there actually is two parts for it. We're going to talk about the logarithm first. For the logarithm, we know that x, the argument has to be positive, so we know that x has to be positive. And in reality, this part is done for us already. But notice that the logarithm is in the denominator of a fraction, so we also have to take into the rule that the denominator cannot be 0. So this is our second rule that we have to do. And in rewriting this, this is log base e of x cannot be equal to 0. In other words, e to the 0 cannot be equal to x. In other words, e to the 0 is 1. I cannot have x equal to 1. So, x has to be greater than 0, but x cannot be equal to 1. One way of writing this is from 0 to 1, union from 1 to infinity. Now this last one was a little bit difficult because we had to combine two rules. But whenever we look at these, you just think about the rule, such as the argument must be positive. That helped us do this first one. And then we had to come up with the other rule, which was the denominator cannot be equal to 0, which gave us our second inequality. And you have to make sure that you take into account all the inequalities to come up with a proper domain. We want to graph each function and its inverse on this axis. So I will go ahead and write f of x with a table. And 1/3 to the negative 1 power is 3. 1/3 to the 0 power is 1. And 1/3 to the 1 power is 1/3. So those are the points we're going to put in. So there's the graph of f of x. Now you might not know much about answering log questions, but we do know that this is f inverse for our f, so we're just going to switch our inputs and outputs. So I plotted those 3 points. I also know that the asymptote, which was at y equals 0, becomes at x equals 0. And there we've graphed f inverse. And notice that these do look like inverses. We can tell because they are mirror image on the line y equals x. Let's draw that line in. So if you tilt your head so that you look at the y equals x line, and you can see that the blue and the purple line are mirror image of each other. Recall that the domain and range of our f function will get switched for f inverse, and that our horizontal asymptote becomes a vertical asymptote. Instead of y equals 0, it becomes x equals 0. And both graphs are smooth and continuous. We can see that they're mirror image on the line y equals x, where all the x and y values got switched. And we see that the x-intercept of 1 becomes a y-intercept of 1, and vice versa, and all the points get reversed. So where we always had the point 0, 1 in our graph, now we always have the point 1, 0. So all of the points get switched and all of the values get switched. For this next question, we're given the function 1/2 log of x minus 5. And the first question we're asked about is to find the domain. And recall that the rule for the domain is that the argument must be positive. So we need to ask ourselves, what is the argument of this function? And when you have log written without any parentheses, we assume that the parentheses is only around what's directly after the word log. So that would be just the x portion, not the x minus 5. And so my argument is x, so I would write that x is greater than 0. And to write that in an interval notation, that would be from 0 to infinity, not including the 0. We're asked to graph the function, so we're going to go ahead and plug in the 3 values that we know. And for our inputs, I'm using multiples of 10 because 10 is our base when it says log with no base. So I'm going to use 1, 10, and 1/10. So filling in our chart, we get these values. We know that the vertical asymptote is at x equals 0, and that hasn't moved with the changes looking at the transformations in our f of x. And we also know that the domain and range are still the same. And so I'm just going to draw this. It's the same shape of the graph that we normally think of with the same vertical asymptote. Part C asks us about our range and our asymptotes, and our range is going to be from negative infinity to infinity, and that's always true. No matter how much the graph gets shifted, even if you go from negative infinity and you shift up 1, it's still going to be negative infinity. Or if you go shift it over 100, it's still going to be to positive infinity. And our asymptote is still our vertical asymptote. If we saw any behavior in our logarithm that changed our domain, we would have moved this as well because it gets affected by our domain, and our asymptotes sort of work in conjunction with each other. But our domain is our standard domain from 0 to infinity, so our vertical asymptote doesn't move. To find the inverse, recall the steps that we're going to do. We're going to write it as y equals. Well, I'm going to switch my x and my y values. And then I want to isolate my y, but to isolate my y, I do want to rewrite it first so that my log is isolated. So I just added 5 to both sides. Now I'm going to multiply by 2. And I now have my log isolated. I'm going to insert parentheses around this 2x plus 10 so that we treat it as one item. And that's going to go in our exponent. Our base is 10. And so I'm going to rewrite this as y is equal to 10 to the power of 2x plus 10. And then I'm going to turn y into our f inverse. The domain and range of this function should be easy. We know exponentials domain is all real numbers, and that actually also works with the inverse of what we had to begin with. And the range of this inverse is 0 to infinity, because that's the domain of our original equation. And it doesn't ask for it, but we do know that we have a horizontal asymptote, and we're going to switch the x to say y equals 0. So that helps us graph it. So knowing that my x and my y values will switch, I have these 2 points here, and the third point just sort of goes off the graph. It's too far to reach. And there is my graph of the inverse. Once again, knowing that it should be symmetric on the y equals x line that we've just drawn, we can see that it is mirror image. These two functions are mirror image of each other. The last few questions in this section ask us to solve each equation, and I'm going to put our formulas down at the bottom. I called them formulas, but it's just the rule. If we have a logarithm, we can rewrite it as an exponential, and so we're given several logarithms that we want to solve, and we're going to do so by rewriting them. So for our first question, the base of this logarithm is x, so I'm going to write x to the power of 2 is equal to 16. And this is something that we should be able to solve. X is going to be plus or minus 4 because we're going to square root both sides. However, which one of these is appropriate to use for this question? Well, we know that the base of a logarithm must always be positive, so we're going to go ahead and throw out the negative 4, and we're just going to keep the positive 4 as our answer. For the next question, it's written as natural log. Remember, the base of natural log is e. So to rewrite this as an exponential, we're going to take that e and take it to the power of 8. And then we're going to put on the other side the argument of the log, which is e to the negative 2x. And then we're going to take that rule, the rule that says if I have an exponential equal to an exponential, then their powers are equal to each other. So 8 is equal to negative 2x, so x is equal to negative 4. Now, is it possible to get negative 4 as an answer? Yes, even though our domain is has to be positive numbers, we know that negative 4, when we plug it in, gives e to the power of 8, and e to any power is going to be positive, so that's fine. But you always want to check against the domain and see if the argument will be positive when you plug that value in. For this next question, we're given a question in exponential form, but we have our variable up in the exponent, and this is not an exponent equal to an exponent like we did in the last problem, so I can't just grab those pieces up. I need to rewrite this as a logarithm to pull the x out of the exponent. So I will get log base e of 13 is equal to negative 2x plus 1. And don't write log base e, write ln of 13. And then now it's just a matter of isolating our x. So I'm going to subtract 1 from both sides. And then I'm going to divide by negative 2. And there's the value. And whenever you're doing one of these solving the equations, you always want to leave it in exact format unless you're told to give a decimal approximation. But at this point, we would be happy with this. Now there's some invisible pieces to this that you might not know. But the 13 is the argument of my ln, and that's fine. But the negative 1 or the minus 1 is not part of that argument. And so you don't want to say ln of 12. And likewise, you're not going to divide the 12 by the 2 because we also have extra parentheses around the ln. You can't break these pieces up. So you have to leave it in this format. You don't need those parentheses or the brackets, but you can't combine the pieces more than what we've done. And that's our solution. Now, if I asked for a decimal approximation, I'll tell you to how many digits I want after the decimal point, but for the most part I do want exact answers, so it's just a matter of isolating the x. I don't want you to solve for x using a calculator. I want you to use the algebraic methods that we just showed you. So to solve this last question, We do have a log equal to a constant, so we're going to use that rule we have down at the bottom, that we're going to take this and rewrite it as an exponential. And we get the base of our exponent is 5, the power is 2, then we get x squared plus x plus 4 as what it's equal to. So we're going to simplify that. And then all we have now is to solve the quadratic. And when we get to this step, this is not something that's easily solved by factoring, so let's go ahead and use the quadratic formula. So solving it using the quadratic formula gives us these two values, -1 plus the radical 85 over 2, and -1 minus radical 85 over 2. Now one of those is positive and one of those is negative, but when you plug it into x squared plus x plus 4, the argument will be positive each time. So it doesn't matter that one of them's negative, we're going to include both of them in this because our argument is positive for both of them, so they're both valid answers. In the next few sections, you'll get practice at solving logarithms and checking your answers against the domain. And so there are some times where we do have to throw some answers out, but you always have to remember to plug it in and see what happens to the argument after you've plugged it in. Not what is my answer or what sign is my answer, but what sign is the argument, right? And the argument must always be positive. That's the one rule that we want to remember. All right, thank you. Go practice and have fun.